A tritium nucleus moves towards a deuterium nucleus as illustrated in the figure. The nuclei initially have the same speed v. The tritium nucleus consists of 2 neutrons and a proton. The deuterium nucleus consists of a proton and a neutron. The proton and the neutron have the same mass m. The 2 nuclei having like charges repel one another. Explain why it is not possible for the nuclei to stop at the same instant. Now the total initial momentum is not zero. The total momentum will be zero at the instant when both nuclei are stopped. So by the principle of conservation of linear momentum, this will not be possible. At one instant during the interaction between the nuclei, they are both traveling in the same direction with the same speed. Calculate this speed in terms of v. So the total initial momentum is 3 mv minus 2 mv, which is mv. So at the instant when both nuclei have the same speed, let's call it v prime. So the total mass will be 5m times v prime. So they equal to the total initial momentum mv. So v prime will be 0.2 v. The velocity time sketch graph of how the velocity of each nucleus varies is shown. The interaction between the nuclei is elastic. Label the graph to show which curve is for the tritium nucleus. So this is for the tritium because the initial speed for tritium is positive. And the times at which each nucleus stops. So the speed is 0, okay, when both of them stop. So this is a time when the deuterium stop, this is a time when the tritium stop. So the time at which they are at their distance of closest approach is given by this point. Now, from time t0 to t1, this is the point when the deuterium stops, both molecules are traveling in opposite directions towards each other. Therefore, the separation will decrease. From time t1 to t closest approach, the deuterium changes direction at t1. So from negative, it becomes positive. So from this time between T1 and T closest approach, both molecules are traveling in the same direction. Now the deuterium is now in front of the tritium, but traveling at a slower speed. Therefore, the separation will continue to decrease. For time greater than T closest approach, both molecules are traveling in the same direction. The deuterium is in front of the tritium, but now is traveling at a faster speed. Therefore, the separation will increase. Hence, the closest approach, when both of them are traveling at the same speed, is the time of closest approach. Determine the final speed of each nucleus in terms of v. So let the final speed of tritium and deuterium be vt and vd, respectively. So by conservation of linear momentum, we have this expression. The speed of closest approach equals speed of separation. Because of elastic collision, we get the second equation. So solving these two equations, we get v tritium is minus 0.6 v and the velocity of the deuterium is 1.4 v.